Alright guys, so today I want to talk about the refrigeration cycle. I feel like there's a lot of different explanations on the refrigeration cycle, and I want to help try to, I don't know, make sense of it all if I can. I feel like maybe some people will get it, some people won't, but I feel like I have a pretty good way of explaining it. So I want to talk about just the basics, the component, the whole cycle, the circuit, and then basically some troubleshooting tips. What does the system look like when it's low? Or what does the system look like when it's overcharged? Or what does a dirty condenser coil look like? Dirty evap coil. Just different scenarios and things that can happen that can make your pressures and certain readings look different. It's just a lot. So I'm gonna try to dumb it down. And how can I make this simple enough where everyone can understand it? Alright, let's grab this, put this up here, grab a piece of wood somewhere, right here, grab this wood. Alright guys, we're going to talk about the basic components of the refrigeration system, the refrigeration cycle. So we're going to break it into three parts. First part is going to be the refrigeration cycle. We're going to go over three parts. The first part is going to be components and identifying those and what they are. The second is going to be the cycle. And then the third part is going to be some scenarios, just different things, right? We're going to go a little in depth. So let's get to it. First thing we have is the compressor, right? That's going to be our pressure increaser. This is what's going to basically increase pressure, manipulate pressure in order to give us a high pressure gas, right? So that's going to give us a high temperature gas. So this is a hot discharge line, guys. You do not want to touch these. As you can see, I've done that a few times. It's not fun. So hot gas, remember this is a hot gas line. That's what I call it, hot gas line. Makes more sense. And then we're going to flow into the condenser, right? Always remember, guys, we're going to flow into the top of the condenser first. Almost on every system, you're going to see that we feed the top of the condenser and we exit out the bottom, right? Always going to exit out the bottom. So once we're high pressure, we're high temperature gas, we're then going to go through the condensing coil, and we're going to have a bunch of fins on there that's going to help us basically reject some heat. And how we're going to do that is we're going to have a condensing fan. So the condenser fan motor is going to suck air through the coil and out, and that's going to take that high pressure gas and we're going to subcool that. We're going to meet saturation, right? Remember that word, saturation. PSIG, converted temperature. Ty Branneman, he's a really good teacher of this. Stop my video now, go check his out if you want to. Really good explanation on all this. But anyway, once we meet saturation in here, we're going to subcool to a liquid, and then we're going to go to our liquid line. Consists of high pressure, high temperature liquid. We have to have liquid in this line. That's very important. We're going to go over that later, but very important that we have liquid in the liquid line. That's why they call it the liquid line. Always remember that, very important. And then from there, we're going to go to our expansion valve, right? Our metering device, our piston, capillary tube, different ones out there. But once we go here, this is going to be our pressure dropper, right? Above it, pressure increaser. Below it, the pressure dropper. So once we drop pressure, we're now going to become a low pressure, low temperature, liquid vapor mix. We're immediately, as soon as we drop pressure here, we're going to start boiling off. It's mostly going to be liquid, right? And then from there, it's going to start saturating, right? And as it saturates, our goal is to go from liquid, right? And as airflow, as your blower motor, your evap motor, blows air across this coil, we're then going to absorb heat in this coil, and that warm air is going to help bring up our saturation temperature and boil off refrigerant. We need the air to boil the refrigerant off. That's then going to change into a low pressure, low temperature gas, right? We need 100% gas here, so we're going to call this our cold gas line, but cold vapor line. We need 100% vapor here so that we can compress only vapor, right? It is impossible for us to compress liquid. It's not going to tear the compressor up immediately. It's not like throwing a wrench into a ceiling fan or something moving. It's not going to just blow up, but eventually it can. I've seen some bad stuff. It can destroy the scroll plate, the compressor valves, depending on the compressor that you have. Liquid is very bad. So that's basic refrigeration components, each line, right? But there's some important things right here, guys. If you notice, we're separated, right? We have a high side, high temperature, high pressure, right? And then we have a low side, low temperature, low pressure, right? But then also if you split it this way, right? If you split it like this, right? We're always gas up here, right? Always gas on the top of the chart. If we go down here, we're always liquid, right? Liquid, high temperature liquid. It's mostly liquid here, but you get the gist of it, right? So there's always an opposite in this, which is really cool if you really look at it that way. And you can see it here, man. It's just everywhere. It's amazing. But then we're going to go over more in depth here, guys, on the refrigeration cycle. So basically, to give you more of a better understanding of it, all we're doing is we're manipulating with a compressor to increase pressure, and we're manipulating with an expansion valve to drop pressure, right? And the whole goal of that, if we combine some airflow, right? That's the number one thing when air conditioning, right? We're conditioning air. A lot of people forget that, guys. Very important. We're conditioning air. We need to start with air. Airflow before charge, right? So if our air's not moving outdoor or indoor, right? No air moving outdoor, high pressure is going to get even higher. If we're not moving any airflow indoor, low pressure is going to get lower, right? Temperature is going to get lower as well. So we're going to go over more in depth of how that works. As we compress into a high temperature gas and we're really hot, that fan is going to come over the condensing coil, right? It's going to create saturation, right? We're going to start changing state and condensing back to a liquid. The whole goal when we do this is we're going to measure at the liquid line, and then we're going to take temperature as well at the liquid line. There's usually a dryer right here. You want to be after the dryer, but we're going to take that measurement, and that's going to give us a number called subcooling. And I'm going to show you a chart here on the screen. Subcooling, right, is basically going to tell us how much liquid refrigerant am I stacking in this condensing coil here, right? So the higher the number of subcooling degrees, the more liquid, the more full this coil we're going to be, right? So always remember with subcooling, we're going to take a pressure measurement here. That's going to convert to a saturation temperature, right? Then we're going to take a physical clamp measurement, which is going to tell us from the outside looking in, hey, did I leave my saturation bubble, right? I want to ensure that I have at least a small column of liquid in here so that this liquid, or so that this metering device can work properly. This one right here. This needs a full line of liquid, and this line needs a full line of liquid so that this metering device will work properly. Without that, all bets are off. You can condemn, you cannot diagnose a TXV, you can't even test a TXV without a full line of liquid, guys. So, very important, right? If we don't have the airflow outside, we can create issues and not have the liquid refrigerant that we need, right? If we're not rejecting heat, it's going to cause issues and not cool the space like we need it to. So airflow is very important outside, just as important as it is inside, right? So very important with the airflow. But, right, we're creating a saturation bubble. And when we're in saturation, we're never changing temperature during saturation. We only change temperature after saturation. And that's why we check that temperature on the line that ensures that we're fully saturated to a liquid and that I have a nice column of liquid stacking in this condenser. We want about a quarter full in your mind. If you think about a condensing coil, think about it being about a quarter full, right? Or maybe a little bit more, a little bit less. That's going to ensure a full line of liquid, right? And that's what subcooling number is, right? The higher the number, the more liquid we're stacking in this condensing coil, right? So it's very important to have that airflow, right? If we don't have airflow, we have cotton, we're going to have super high pressure, right? And we're not going to be able to reject heat. Your temperature split's going to be off. Everything's going to be off. I'll show you a screenshot here of a really bad unit. When I walked up to this thing, man, it was like a bomb. Very scary. So, as you see in this number, It is very important that we keep this clean. We ensure that we have good airflow across this coil before we say any judgment on refrigeration. Before we measure refrigeration and say there's any issues, we need to make sure everything's clean, right? You can also measure and see that that's a problem, right? If we have a condensing temperature of 130, 140 degrees, that's super hot. There's certain ranges. As you work on the equipment, you will notice that at different temperatures during the day, the more you do this, the more you understand this process, the better you're going to realize that hey, temperature and pressure really do go hand in hand, right? If I don't have airflow and I create an environment of really high temperature, I'm going to create an environment of really high pressure, right? And I'm going to start wearing components out, and I'm going to create premature wear on that equipment, more downtime, just really bad stuff, right? So very important there. So once we establish that liquid column, right, and we leave the condensing coil, we're then going to work our way out to the metering device. We're going to go through a liquid line dryer, which is going to help get rid of moisture or anything contaminants. Not really contaminants, but moisture is the main thing it gets rid of. But after that, we're going to go to our expansion valve. The expansion valve is going to take that high pressure, high temperature liquid, and it's going to drop pressure, right? Just like an aerosol can. So I'm not going to spray this, but if the contents in this were very high pressure like they are, if I were to spray this like an aerosol can, air duster, when you do that, notice how you feel that cooling effect, that really cold air. When you make a drastic change from super high pressure, what's in this can, to atmospheric air, what's around us, which is very low pressure, that's going to create a cooling effect that we need. So basically, that's what this expansion valve is. It's like a can dropping pressure, right? There's a valve in here that takes this high pressure, drops it out to ambient so we can use it for painting, dusting, whatever we need to do with it. But in our case, we're going to use this expansion valve to drop pressure, to manipulate refrigerant saturations, to get it to do what we want it to do, right? And the whole goal of it is absorbing heat in this coil and rejecting heat in this coil. So again, once we drop pressure and we become that low pressure, low temperature, liquid vapor mix, airflow is very important, guys. Remember, we're going to go back to airflow. Important outside, just as important inside, right? Almost, I want to say it's almost equal, but I want to say indoor is a little bit more important for some reasons, but I'll get to those reasons in a minute. But we need that air to go across this coil. It's the temperature of the air and the physical amount of the air that matters, right? So if you've gone to school, if you're in the trade a little bit, you should all know we need about 400 CFM per ton, right? 400 CFM per ton of cooling. So for 12,000 BTU, we need 400 CFM. So if we don't have that air, that physical amount, or the temperature is too cold, we will not boil off refrigerant, right? We're going to stay in saturation too long, right? Same thing over here. If I can't condense this and cool it to a liquid, I'm never going to leave saturation, and I'm going to have a really low subcooling number, which is going to affect my charge. And it's not always low charge that does that. It could be airflow as well. In some cases, airflow on the condensing coil can actually artificially raise your subcooling, which is crazy, but you will see that. That's why ensure things are clean before you make a judgment on charge. Same thing with indoor, obviously very important. So as we absorb that heat, we need plenty of heat so that when we fill this coil with low temperature liquid vapor mix, and as it's boiling off with the help of airflow and the refrigeration circuit, we are going to start boiling off refrigerant, right? We want that saturation bubble almost completely in this coil, except for, right, the top part of this coil. We want to start changing temperature, which means we're leaving saturation, right, guys? Because during saturation, we're not changing temperature. But once we leave saturation, we are changing temperature. So we'll take a pressure measurement on the suction line, right? And then we'll take a temperature measurement on that suction line. And we're going to see a low pressure, low temperature vapor or gas. Well, when we take the pressure measurement, that tells us how big is my saturation bubble. If I have a really low saturation, my saturation bubble's tiny, right? That means I'm too cold too soon. All that air boils off the refrigerant. I have an empty void of refrigerant here, and I have too much hot vapor, too much superheat, right? So, opposite of the condenser, guys, the lower the superheat, the more filled of this coil of liquid refrigerant we are. The higher the superheat number, the less we're filled, right? That means we're saturating too low, we have an empty void, right? So lower the superheat, the more flooded the coil is. The higher the superheat, the more starved the coil is. That means we're boiling it off too fast, we got too much vapor, too much superheat, right? You can have a blower speed that's too high that causes too much superheat. You can have a really high load inside that's causing too much superheat, depending on your metering device and what you're looking at. So many different scenarios, guys. That's how that works, right? We're manipulating the pressure, right, to create a saturation bubble to absorb heat, and then we're gonna capture that heat, right? We're gonna basically close the doors on that heat. Once it absorbs and goes into this coil, right, we're gonna leave saturation, which means we're closing the door. We're gonna take that heat and it's gonna hit a ride on the refrigerant, right? That heat is now trapped in the refrigerant. Once we leave saturation, the compressor is then gonna increase the pressure, manipulate the saturation bubble again, and we're gonna create saturation, and we're gonna take that heat that we captured over here, and once we open up the saturation gates, bam, the heat is gone. The heat will now leave the door. It's gonna now go outside, and thermodynamics, right? Hot air will always attack cold air. So it could be 95 degrees outside, we're gonna make this coil hotter than 95, we're gonna cool the refrigerant and reject the heat outside. So that's possible, right? That's what this manipulator does here, the compressor, the pressure increaser. Opposite of what this does, but right? There's an opposite, right? Almost the same thing, but different. But always remember, guys, your low side is inside the home. That's the cool side. The high side is usually outside, right? It's your condensing coil. That's the high temperature stuff. So, but very important. I'm gonna go over one or two more scenarios, right? If I have really low airflow and I'm running the temperature too low, let's say 65 degrees in the house, dirty filter, this coil right here is gonna be basically filled with saturated refrigerant. It's gonna be saturated. It's gonna be completely filled with liquid refrigerant. It's in saturation. It's not fully liquid, but it's in saturation, right? So we're gonna have a really low superheat number, right? Because we don't have any airflow. We need that warm air to boil that air, or to boil that refrigerant off, to get us that superheat that we need, right? It's gonna keep the pressure up on that coil, right? Keep us away from 32 degree saturation. Keep us away from that danger zone, right? So we need the airflow. It's very important, right? We have to have the airflow. So remember guys, it's the physical amount of the air and the temperature of the air that matters, right? If we don't have that, we're not gonna boil off refrigerant, right? So in some cases, you can have a 32 degree suction line and a 31 degree vapor saturation in your coil. That tells me when I pressure up to this line, that port gives me a 31 degree saturation. That tells me that I'm saturating at 31 degrees, but I come out here and I'm only 1 degree out of saturation. That tells me I'm not boiling off refrigerant. And if I'm not boiling off refrigerant, I need to know why, right? Because this compressor can only compress vapor. This compressor cannot compress liquid. So that's why it's very important, right? So our whole goal in the refrigeration circuit is to protect this compressor and to ensure that this expansion valve has a full line of liquid and that our air circuits are working and clean and it's set at the proper speed and rate. So same with the condenser, it needs to be clean, the fan pitch needs to be set, you need to have the right motor in there, you need to check for universal motors. Different things can affect that number, right? If your fan pitch is bad, it's going to cause air to just roll around in the coil, get too hot, and you're not going to basically condense back to a liquid. Same thing with the indoor. You can put too small of a blower, set the blower speed too small or too high. If you set it too high, you're going to boil off too much refrigerant, right? It's going to cause comfort issues. If you drop the blower speed, it's going to drop the pressure a little bit, but you're going to get a little bit more dehumidification, right? Because if we drop that blower speed, we have more air time across that coil. Depending on your climate and your area, you're going to have better dehumidification, right? You're going to get rid of that moisture in the home. I live in the Southwest. I don't have to worry about that. But for you guys that are out there, I feel bad for you, man. I'm very lucky that I live in the Southwest and I don't have to deal with that. But we all need to be educated and trained and know that, hey, in those climates, that is important, right? We can't have mold in the house. So if I ever move to Florida, I need to know that. That's why it's very important to know this no matter where you live. Because some contractors in dry climates will get away with doing this incorrectly, right? They're gonna put a 5-ton system with very small ductwork on the very small house as well. And then it's gonna basically short cycle. It's gonna cool this space down tremendously fast, right? We don't get any dehumidification, but we don't really care because we don't need it here in this dry climate. But those days that we do need it, the very few, she's gonna be a little uncomfortable, but she may not notice it, right? But if she doesn't notice it, she's not gonna notice what's happening internally, right? The customer's not gonna notice what's happening internally, the bad stuff. So those contractors get away 10, 15 years down the road, and we have a grounded compressor, and we wonder why, right? If we don't have the airflow, we can't boil off refrigerant. If we can't get back to vapor state, compressor is gonna get damaged, right? It's gonna get slugged with liquid. That liquid's gonna start washing lubrication. It's gonna tear things up. So very, very important, guys. Airflow is just, it's extremely important, indoor and outdoor. That's why I say it's slightly more important indoor. Really tear the compressor up. You could tear it up pretty fast on the outdoor unit, but usually systems will have protection to prevent that. So that's why we preach maintenance to our customers, right, guys? To prevent a lot of these issues that affect this refrigeration cycle, this entire circuit. So always remember, guys, you have a refrigeration circuit working in tandem with 2 air circuits. You need to ensure that everything is clean and moving correctly. And you need to understand that, hey, airflow can affect indoor refrigeration pressures and temperatures. Airflow can affect outdoor temperature pressures and things like that. So hopefully this helps you. Let's go over it one more time, guys, and then we're gonna be done with this. So as we go through the cycle, the compressor is gonna manipulate the pressure, bring it higher, right? We're gonna go through the condensing coil. We're gonna create our little saturation bubble. That saturation bubble we're then gonna use to reject heat that we absorbed inside. And then from there, we're gonna basically subcool to a liquid for our metering device that needs liquid, all right, guys? Then from there, we're gonna drop pressure. Once we drop pressure, we're then gonna become a pressure, low temperature vapor, and we're gonna use that low temperature vapor mix that's in saturation to absorb a lot of sensible and some latent heat. And we're gonna take that heat, and once we get out of saturation, that's basically closing the door for that heat to leave, right? We're gonna take that heat and we're gonna take it back through the compressor. It's gonna manipulate everything again to create that saturation bubble so that we can release that heat again back outside that we just absorbed from inside. And then we're gonna just do the circuit over and over again, right? So as this is flowing, right, we need to make sure that this is flowing, this air is flowing, and that this air is flowing, right? Everything's gonna affect each other, right? Everything. So we'll go over some more scenarios later. I just wanted to give you guys a little gist and show you my cool little thing I built. I figured this would be a whole lot better to explain to everybody just how the circuit works and everything. So if you guys want one of these, please let me know. I can make them. I think we're charging $1 a minute or something on the laser. I forget what it is. So I think this one is about 175 bucks if we were to charge somebody to do it. Paint and everything. So, but anyways, if you guys want one, hit me up in the messages, direct message me, DM me. If you guys want one, I can definitely build one. Put your company logo on it, whatever you guys want. Just let me know. But hopefully, guys, this helps you. But if you guys want to, check out my channel. I do have some service work on there. I'm just trying to grow the channel. Just try to give as much information as I can and help the community, help the HVAC industry out, and do my part. Do right by the customer. You got to understand this stuff to do right by the customer. So but that's about it, guys. But if you want to look at service videos, like, comment, subscribe. We're out of here.